what I really want to show you here, which I'm super excited about, even though this is a heat transfer course, but because we're talking about energy balances, I want to show you how in fluid mechanics they derive their pump equation using the same open system energy balance that we use in our heat transfer applications and also in our thermodynamic applications. Because one of the things that I find often is because you have different courses in university. So you have a fluid mechanics course that just teaches you about, for instance, pump sizing. And so you don't get a chance to appreciate or realize that the energy equation that you're using in this class comes from the same place of the energy equation that you're using perhaps in your thermodynamics or heat transfer class. So I'm hoping to take a moment now so that we can take a step back and be able to see that this energy balance equation is universal. And from it, then you could apply some assumptions and reach to these energy balance equations that you're used to using. So let's look at this pump and let's look at this control volume. So let's say you have a control volume over here around this pump. And let's say this is a liquid pump. So you have water that goes into the pump and you have a shaft that then gives energy to the liquid and pushes water at the outlet of the pump. Now, this is the energy balance equation that we've already talked about extensively. So I'm not going to go over the terms, but I'm going to go over some assumptions that we do make in fluid mechanics to eventually reach the pump equation. First, we assume that no external heat is added or no heat is removed from the system to the surroundings. So that means this Q term is 0. Then we assume that no energy is generated inside the control volume, as in there's no electrical, no chemical, no nuclear energy generated, and therefore this term Eg would be 0. We also assume that for a pump, it is running at steady state. It's an open system steady state process. So that just means that there's no energy accumulation inside the control volume, inside the pump. So that means any energy that is being added to the fluid by the shaft is leaving with the fluid as it leaves the pump. And so if we look at this energy balance equation, inside the control volume, we said we're assuming it's steady state. So any energy that's being added by the shaft into the fluid is leaving with the fluid. So energy rise inside the control volume is 0. And we obviously said that, there is no additional heat that is added or removed from the system to the surroundings. So that is 0. And we said there's no energy generation inside the system, so that is 0. Then we have the shaft work, and this shaft work represents the work that is being provided by the shaft that's being added into the fluid, so we're going to leave that. Now, if you look at our energy balance, what we have is we have the energy of the fluid coming into the pump, which is represented by this term over here on the left-hand side. Now add to that the energy that's being added by the shaft inside the pump. Now the sum of both of them will have to equal the energy of the fluid leaving the system. And this is basically what this energy balance is telling us. So you already have some energy that's being added into the control volume, which is due to the flow rate of the liquid coming in. But however, there is additional energy because of the shaft that is being provided to the fluid, and all of that will be coming out. So all of that is equal to the flow rate, that is the energy of the flow that is leaving the system. And so this is what this equation means. Okay, so you probably now understand what this equation means, but this is yet not what you see in your fluid mechanics class. So let's do further simplifications. Okay, so this is the equation that we stopped at. Now, for a pump, we know that the mass inlet and the mass outlet are the same because there's no accumulation of mass inside the pump. And if you expand, you will get this expression. Now, if you divide all the terms by the mass flow rate, what you get is the internal energy plus at point 1, which is the inlet, plus the pressure at point 1 multiplied by the volumetric density at point 1. plus the velocity at point 1 of the fluid coming in, which is the kinetic energy portion, so the velocity squared over 2, plus the potential energy of the liquid at the entrance point, which is just the gravitational constant multiplied by Z1, which is the elevation of the entrance point relative to a reference, plus the additional work that's being provided by the shaft divided by the mass flow rate, will equal to the internal energy of the fluid leaving at point 2, plus the pressure at point 2 multiplied by the volumetric density at point 2, plus the kinetic energy at point 2, which is the velocity squared over 2 at point 2, plus the potential energy at point 2, which again is just the gravitational constant multiplied by the elevation, the point of elevation of which the fluid is leaving the control volume at. So all I did is I just expanded this. Now I want you to realize something. For incompressible fluids, volumetric density is not sensitive to pressure and temperature. Therefore, if you look at volumetric density, which is just 1 over density, really, across different pressures and temperatures for incompressible fluids, and that is how incompressible fluids really got their name. So like if you look at charts for the density of water at 20 degrees Celsius and 40 degrees Celsius, it will hardly change. Also, if you look at the density of water at like 100 kPa, like 1 atmosphere, let's say, versus 2 atmosphere, you'll see it hardly changes. And that's why we can make this simplification where we could assume the volumetric density of the water at the inlet and the volumetric density of the water at the outlet is pretty much the same. So we're just going to, instead of noting it 1 and 2, we're just going to say capital V. And in this case, if we substitute that into the equation, and if we actually express the volumetric density in terms of mass density, the volumetric density equal to 1 over the mass density. So if we substitute that into this equation, now this is what we get. And if we rearrange to solve for shaft work, which is essentially the work of the pump, we will get this relationship. And if we divide by gravity, we finally get this expression, which is essentially shaft work expressed in length. So if you look at the units of this, you'll see that the shaft work over here is expressed in units of length. And if you look at each of these terms, you're going to see that each of these terms are also expressed in length. And do you remember, if you look at a pump curve, for instance, you see pump curve expressed in length versus flow rate. And that is essentially this term over here. And what I did is I grouped the like terms. So the pressures, I've grouped them together. And what this shows you is that, P2 minus P1 is the contribution of the difference in pressure, or sometimes called the pressure head. And the difference in velocity is also the sometimes called velocity head. And the difference in elevation is also sometimes called elevation head. And now you have this term that you probably are confused with what this term actually means. This is the difference in the internal energy of the fluid. So let's try to massage this expression so that I can show you the expression that you are used to seeing. So now we've reached a point where we were looking at this equation, and I said the shaft work is expressed in length. Now, and as I said, I grouped these terms to put the like terms together. So as I said, P2 minus P1, which is the pressure at the outlet minus the pressure at the inlet, is the flow work, but it's also called the pressure head. Similarly, the kinetic energy head is the difference in the velocities, and their velocities to the power of 2, difference in them, divided by 2g. That represents the change in kinetic energy, and the change in potential energy from the inlet to the outlet is represented by Z2 minus Z1, and the change in internal energy is represented by capital U at point 2 minus capital U at point 1, and that is divided by gravity. So in this system that we're looking at, we said there's no external heat transfer, right? So you can consider it an adiabatic system. We said Q was 0. So in this particular system, the internal energy changes, they arise from the viscous dissipation, which is the friction due to the flow resistance in pipes. So as the flow moves in pipes, you have the mechanical energy of the system starts being eaten and consumed due to the resistances that you face because of the flow in pipes, and that change will result in heat that will be absorbed by the same fluid. And so now what happens is you just have a conversion of the mechanical energy, which is the useful energy that you need to push the fluid inside of pipes, now being converted to friction, which is heat essentially that will be absorbed by the fluid. And so the temperature of the fluid will rise, and that is what this internal energy change is capturing. So the last term represents the conversion of mechanical energy into thermal energy due to the phenomena of viscous dissipation. Now in practice, this effect is captured using a frictional head loss term, sometimes noted as HL, where in this particular application, with all of the assumptions that we've made, HL over here represents the change in internal energy divided by gravity. And you can calculate this frictional head loss using empirical correlations once the piping configuration is known. So you know how for instance you use the Darcy equation and you use empirical correlation. So if you study fluid mechanics, you know what I'm talking about. You essentially calculate all of these frictional head loss terms to be able to calculate what the total frictional head loss you need the pump to be sized for. So therefore, if we look at the pump equation that you are pretty much used to, it's P2 minus P1 over rho G, which is the difference in pressure, the pressure head, plus the difference in the kinetic energy, plus the difference in the elevation head, plus the additional energy that you require to push against all of the friction losses. And that is the sum of all of that is the amount of energy that you need to ensure that the shaft work can provide. You need to ensure that the pump is sized strongly enough that it could provide this energy, which is the sum of all of these terms. Now, you can use this equation to size liquid pumps because it represents how much energy the pump needs to supply so that the fluid can reach eventually where it needs to go at the right pressure, at the right velocity, at the right elevation, and has enough energy to overcome all of the friction losses in the piping that you have. So I'm very happy to have showed you in this video how we started from the open system energy balance equation, the general equation, to the particular application of sizing a pump using the energy balance and seeing through the assumptions that we use. Now, at least, I hope that you can make connections between what you studied in heat transfer, thermodynamics, and what you study in fluid mechanics. And by the way, if you really want to master fluid mechanics and know how to size pumps for real-world applications, this is something I'm very passionate about and interested. I have a lot of experience in industry. You can see a course that I've developed that is focused on teaching you how to size pumps for incompressible fluids. And you'll see how to calculate the frictional head loss and how to size pumps and how to look at pump curves and how pumps are made and what are the different methods that you can control the flow rates in a pump and all of that. But anyways, this is a course about heat transfer, but I just wanted to show you that relationship because what matters mostly to me is that you understand the concepts than just applying blindly, because that is not good, especially if you're trying to be a very strong engineer. You have to learn and understand the fundamentals. Anyways, without further ado, see you in the next video.